In part 3 of this volume series, you'll probably first notice that there's a costume change. These were recorded out of order. But in part 3, we're going to discuss another way of how to find these volumes of solids rotated around lines, okay, and that's going to be through the method of shells. As I mentioned in the disks video, sometimes we might have to slice up our regions in a slightly different way. You also saw that with area between curves. And we'll demonstrate that with shells, sometimes we can slice up our regions in ways that make our life a little easier. And towards the end, we'll be able to see that, like, no matter how we slice it, if we set up our integrals correctly, we'll still get the same numbers. So let's go ahead and get started. So before we begin, okay, we need to first figure out, well, what's our basic formula for shells and what's the idea? Well, the volume for shells here, okay, right up here, 2 pi times an integral, and these will be generic placeholders, shell radius times shell height and dx, or whatever variable you're integrating with. Now, where does this formula come from? Let's go ahead and demonstrate this with the first example. We want to rotate this solid, this region rather, bounded by this curve, y equals e to the minus x squared, okay, which is in blue, which, by the way, for those of you that have taken statistics before, this is familiar, the normal distribution, or as you'll probably hear it called, the Gaussian, okay? It's going to be bounded by y equals 0, so that is the x-axis, okay? The lines x equals 0 and x equals 1, so let's go ahead and draw those in. X equals 0, x equals 1, so this little chunk here, our usual thing of coloring in our solid body in magenta, but now we're going to rotate this around the y-axis, okay? So let's go ahead and draw an arrow here. Where the y-axis is the line x equals 0. And we'll go ahead and rotate it around this line here, this obnoxious bright green. Now, we're going to go ahead and do this with the method of shells here because the method of disks would be a little obnoxious here. Well, because if I do disks, remember with disks, I want to rotate slice perpendicular to my axis of rotation. Well, I have two regions here that my strip's going to pass through. I'll have this little rectangular region here, and this part here from the bell curve out to the line x equals 0, which requires me to write two integrals. And then, of course, inverting this thing is probably going to be a chore. I might have to worry about some other domain restrictions. That's no fun. So we're going to go ahead and scrap that idea. Instead of slicing perpendicular to the axis of rotation, we'll go ahead and slice parallel to the axis of rotation. So I'll go ahead and do this in blue. Instead, I'll go ahead and take this strip here in blue. I'm going to go ahead and take a slice here. And imagine, if you will, I rotate this around my axis of rotation. I get something that sort of looks like this. Okay. And I get this kind of cylinder here. Okay. But what does a cylinder have anything to do with volumes? Well, we know how to find the volume of a cylinder, right? Pi r square h. But how does that really help us here? To imagine this, we need to first remember what we're really doing with these volume questions. Okay, we're finding little areas, and these areas are going to be perturbed a little bit and made with a small thickness, and then we're going to somehow glue, or in this case, nest these areas together. So to demonstrate that, if I can find something here on my desk, or maybe, here's a sticker of mine. Okay, actually, let's go ahead and come back out here to the solo camera here. I have a sticker. Okay, one of my favorite bands here. This is a rectangle, but if I go ahead and glue those edges together, I get a cylinder. Now, I haven't really changed the shape, but the lateral surface area out here, okay, this is this white face here on the outside. That lateral surface area is the same as the area. Oh boy, I bent it. Yeah, that's fine. That's the same as this area here on the white side. Base times height in the rectangular sense. That base gets wrapped around into a circle. So we got to think about the circumference of our circle. That's the 2 pi r, 2 pi times the shell radius that you see up there. Okay. So we need to figure out our shell radius and our shell height. And now here's going to be our procedure for how to do this. Okay, we need to know that for shells, okay, the shell method will combine both the top minus bottom and right minus left principles from area between curves. So for the radius, okay, the radius is going to be the distance from a strip here to the axis of rotation, which I've drawn here in gray. That distance there is the radius, okay? And the way we're going to think about this is that our axis of rotation, which is there in black, let's go ahead and make that a little more prominent, okay? This is our axis of rotation, and our strip here is varying. So the strip will be at some location, let's call it X. And of course, we have our axis of rotation here at X equals 0. And so what is the distance from any strip to the axis of rotation? Well, let's write it down here. So the radius here, think right minus left, x minus 0, or just simply x. And then from the picture, what is the shell height? Well, the shell height here, think about it. Top of the rectangle to the bottom of the rectangle. Top minus bottom, right? Just the same stuff that we've seen before. Simply e to the minus x squared. Okay, and now we'll build our integral here, okay, for our volume. 2 pi times the integral from 0 to 1 of x times e to the minus x squared dx. Now we might look at this and say, that's a little funny. I don't know how I can probably integrate that. You got the tools, okay? You got the tools to integrate this, all right? In fact, we can do this by a u substitution, okay? Go ahead and make the u substitution here. Let u equal x squared. Probably the best way to go about it, to let u equal x squared. Du is now just simply 2x dx. Okay, we've done substitutions a number of times, so this should be kind of second nature. Okay. The 2x dx here, normally I would go ahead and divide both sides by 2 and get the perfect matching here, but I already have a 2. Okay, notice that I already have a 2 out here, right? 2x dx. That's all going to collapse into my d. Okay, but remember that we also need to change our units. Okay, so let's do it in this color here. So when x is equal to 0, okay, we get that u is equal to, well, plug it in to our substitution. 0 squared is 0. Likewise, when x is equal to 1, well, u is 1 squared, that's just 1. So our region of integration actually didn't really change. But we still have to go through this and make sure we change our units, okay? They have different meanings. So let's go ahead and write our new integral here. Go back to black here. So we'll have pi, because I'm going to absorb that 2, okay, into my dx, into my du, excuse me. Pi times the integral from 0 to 1. Now 2x dx, remember, is just du, okay? And now I have e to the minus u du. And remember, integrating exponentials is pretty easy, right? Remember, when I integrate an exponential, I always get a copy back, okay? And that always comes back to differentiating exponential. Let's remind you of that fact here in Roadrunner Orange here. So remember that the derivative of e to the kx, let's do that for general k, okay? Here k is negative 1 in our case. Well, the derivative here, we'll get a copy back. And then by the chain rule, we multiply by the derivative in the exponents. That's just k, right? You might see this kind of thing pop up again if you take linear algebra and different equations. And word eigenvalue and eigenvector will come up. But anyway, okay, that's how we handle differentiating the exponential function. So integrating it is in a similar fashion here. Instead of multiplying, we divide. So an antiderivative, let's go ahead and scroll up a little more. There we go. Antiderivative e to the minus u is just, well, minus e to the minus u. Now we evaluate that between 1 and 0. Okay. And now we just go ahead and plug in minus e to the minus 1. Okay. And then negative, let's just be careful there. Okay. Negative e to the 0. Okay. And if we tidy this up, okay, well, e to the 0 is 1. Negative, negative is a plus. So this will be pi times 1 minus e to the minus 1 You could also write that inside as 1 minus 1 over e, but I think this gets the job done. And that's our volume. Okay, that's our volume by shells. If you are so inclined, you can also figure out how to do this by disks. It's going to be a little harder there. But this is just a method of convenience here. Just another way to slice up our little area here, okay? Think about rolling these things, okay? This little blue cross section here, you're viewing that from the side, okay? Think about rolling these like paper tubes up. Let's do another. Here's our other picture here. Okay, we're going to rotate this region here bounded by y equals x squared minus x cubed. That's the curve in blue. Okay, the line y equals 0. So let me go ahead and put that in bold here. The y equals 0 is the x-axis. There we go. Okay. And we're going to go ahead and color that in magenta. Okay, and we're going to rotate that around the y-axis. So let me go ahead and color in where the y-axis is. Okay, so we're going to take that magenta area and rotate that around the y-axis. Same color. All right. So now again, we got to think, well, what would a typical shell look like? Let's do that again in blue. So this is a little strip here. Remember, we're going to slice parallel to the axis of rotation. Here we're rotating around the y-axis. And our little shell here, okay, it looks something like this. This is where a little shell would probably look like. Imagine like a little bundt cake. Okay. That's what our little shell will look like. So again, we got to think about shell radius and shell height. We also got to think about where this thing intersects here. Clearly right there and right there. We can see on the graph, yeah, it's x equals 0, x equals 1. But again, you should show that, right? How do we do that? Well, we want to find the zeros of that function there. Let's go ahead and do that. X squared minus x cubed equals 0. I have a common factor of x squared that I can factor out, so I have 1 minus x. And of course, just by using the zero product property, we have x equals 0 and x equals 1. Okay? And if you need a refresher on that, you can always consult your favorite algebra text, your favorite pre-calculus text. Okay, it's just factoring. So we have our x limits of integration. Now let's also go ahead and fill in what our radius and height would be. Again, the shell radius will be the distance from a strip to the axis of rotation. In this case, we'll be using the right minus left principle. Well, the strip is located at some position x, and the axis of rotation is the line x equals 0. So the radius is just x. And the shell height, well, think about the picture again. Top minus bottom, just area between curves, right? X squared minus x cubed. And now, set up our integral for the volume. Just follow the recipe. 2 pi times the integral from 0 to 1. Okay, that's our x limits of integration there. Shell radius is x times the shell height, x squared minus x cubed, dx. And just multiply out, use the power rule. Let's go ahead and do that, right? So when we multiply the x through, we get x cubed minus x to the fourth. Okay, go ahead and scroll and use the power rule here. So we add 1 to the exponent here, that 2 pi factor. So x to the 4 over 4 minus x to the 5 over 5. Evaluate between 1 and 0. And thankfully, evaluating at 0 will give us 0. So what are we really left with? 2 pi times a fourth minus a fifth. And if you use a calculator, or you can work it out here, well, a fourth, a common denominator would be like 20 here. So a fourth is 5 over 20. A fifth is 4 over 20. Okay, you'll have 2 pi times 1 over 20. And the volume you need is pi over 20. Now, if this part here tripped you up as I was kind of talking my way through it, that's okay. Just use a calculator. That's okay. That's what they're used for, right? Just make sure that you put the grouping symbols where to go, right? Okay, get a common denominator and all that. Pi over 20 is that volume that you can also do the little, if you know about a cross multiplying butterfly, the nice multiplication shortcut way of being lazy, of adding and subtracting fractions. So you see, this is just another way of doing this volume thing. Again, if we use disks here, it would be a little annoying here. We have two integrals to compute, and of course, this function here doesn't emit a nice inverse, okay? If I were to go ahead and chop this perpendicular to the axis of rotation, okay? Well, this guy doesn't have an inverse, okay? So I'm going to have to worry about some domain restrictions here. Using shells helps me avoid all that. Let's keep moving. One of our favorite shapes, a parabola, okay? Okay, we have the parabola, the line y equals 9, so let's go ahead and throw that in here. I'll throw that in orange here, just really the top line here, okay? And then we're going to rotate this around the x-axis, so I'll go ahead and bold where the x-axis is. Okay, so the solid formed by rotating the region bounded by y equals x squared and y equals 9, so that's going to be this whole inside of the parabola here. Lots to color in. Okay, we're going to rotate this around the x-axis. Okay, we're going to rotate it around the x-axis. Now, looking at this question, okay, as I was preparing for this, I'd say, disks is a little more natural here. But since we're looking at the shells here, we want to go ahead and demonstrate how to use shells here. Let's go ahead and figure out how to use the shell method here, okay? So with shells, instead of slicing perpendicular to the axis of rotation, so if you were going to use disks, you would slice up and down so that you have a strip, say, oriented like this. Okay, that would be for disks, okay, because that's perpendicular to the x-axis. For shells, we want to slice parallel. So I'll draw in one small slice here. Actually, let's go ahead and make that a little bold. There we go. Easier. Okay. And we'll draw in like what a representative shell would look like. Okay, now you see we're going to have to think a little differently here. Okay. Instead of our integrals usually being in x here, now we're going to have an integral in y because this strip moves up and down. Okay, so how do we handle that? Well, we got to think again still shell radius and shell height. If you turn the picture on its side, you can think about it so that way. Remember, shell radius is going to be the distance from the strip to the axis of rotation. Okay, this guy here is the radius. And let's choose a different color here with this red. This is the shell height. Okay. But for the shell height here, observe, okay? Because the strip is now horizontal, it means I'm integrating in y, so I need a function of y. Okay. We're going to go ahead and take y equals x squared. I'm going to invert that by taking square roots here. By taking square roots, we'll get that x is equal to plus minus square root y. I'll go ahead and label here. And the right half here, we have the plus branch, plus square root y. And on the left half, we have minus square root y. Okay. So now let's think about what the shell height's going to be first. That's probably going to be the hard part out of the way. I'll do it in the same color. So shell height is really the width across here. Now we got to think right minus left, okay? Well, we have square root y minus a negative square root y. Okay, right minus left. The left half of the parabola is minus square root y. Well, minus minus is plus, so we get now 2 square root of y as our height. And our shell radius, all right, well, let's think about it. It's going to be the distance from the strip to the axis of rotation, and here we're thinking top minus bottom. The top minus bottom here, the strip is varying at some position y, okay, and the axis of rotation is aligned y equals 0, the x-axis, so y minus 0, y. And now what do we do? Just set up your integral, right? Remember that formula that we had before? I'm not going to copy it again, but go back. Same deal here. Except now instead of integrating in x in this one, we're going to be integrating in y. Let's build our integral. Our volume that we need is 2 pi times the integral from where to where? Well, from y equals 0 to y equals 9. Okay, think about moving that strip up and down. Okay, the shell radius, which is y, and the shell height, which is 2 square root y. Y. Now it's just going to be a game of shuffling some things around and, hey, what's the same punchline? It's the power rule, okay? It's the power rule, right? Let's do some shuffling of constants. Well, the extra 2 inside, I will absorb that into the 1 outside. That's a 4 pi. We fix that integral sign. Okay. But y times square root of y, okay. Remember, y square root y, that's the same as y times y to the 1/2, and we add the exponents, right, when we multiply. So 1 plus a half is 3/2. And there's your power rule, right? All right, so we'll have a 4 pi, and thankfully, the evaluation at 0, I can already see the evaluation at 0 is going to be 0, but let's write out everything. Y to the 5/2, that's 5 there. Then we're going to divide by that new exponent, but dividing by 5/2 is the same as multiplying by 2/5, okay? Keep, change, flip, right? Okay, now if you're ever unsure about your antiderivative, just go ahead and take the thing that you think is the antiderivative, this guy here that I'm highlighting, take the derivative. You should be able to get your integrand back. Okay, derivatives and integrals are inverse processes. Okay, that's what FTC is, right? Okay, so we're going to go ahead and evaluate this. Okay, again, the evaluation at 0 just ends up being 0. Okay, so we'll have 4 pi times 2/5 times 9 to the 5/2. Okay, and then minus, that stuff evaluated at 0, but 0, square root of 0 is 0. Okay, and 0 to the 5th power is 0. Okay, well, if we use our handy-dandy calculator, right, 9 to the 5/2. Okay, and make sure that we are actually typing these things in correctly. 9 to the 5/2 is 243. Wow. Okay, so I have 4 pi times 243/5. And I don't think that simplifies. I was like, I can cancel any common factors. So yeah, we'll just go ahead and write that in a final form. 972 pi over 5 after we multiply everything out. Chabow. That's your volume. Okay, don't let the numbers scare you. Okay, notice that here, just a power rule. Okay, we can, again, cast this for different kinds of functions. Okay, we'll soon learn for our other integration techniques that you can still do the same exact thing. Going. We're on a roll here, right? All right. This one's also going to demonstrate that you should read the descriptions of your regions to make sure that you're coloring the correct one here. So, find the volume of the solid generated by rotating the region bounded by y equals square root x, that's in blue, y equals 0, that's going to be the x-axis, x plus y equals 2, that's this line in this off orange color. We're rotate around the x-axis. So, let's think about what this region is. Okay. So, I'll first go ahead and hold in the x-axis. And now let's think about which one of these 4 pieces to color in, okay? So we have the region bounded by the square y equals square root of x. That's the blue curve. Okay, let's actually trace this out with the mouse so you all can see. So the blue curve, y equals square root of x, y equals 0, which is the x-axis, and the line x plus y equals 2, which you can write as y equals negative x plus 2. That's this orange line here. So we want it to the region with those curves as boundaries, so we're clearly going to go in this little bottom part here with the tip pointing up. So let's go ahead and color that part in. Okay, and we are going to be rotating around the x-axis. And once again, we want to use the shell method here. Okay, discs does feel a little more natural here, but if you think about this, if you integrate an x, okay, think back to the area between curves video, right? They intersect, you have a bow tie shape. So I have to split this into two integrals. That's going to make things a little messier, but with shells, I can actually do this one integral. Okay, so let's go ahead and draw in our representative strip here, probably up here. So, okay, and once again, I'll go ahead and draw in this little representative shell here. I won't necessarily do that for all of them. Okay, it's not a good picture, but it's a picture nonetheless. Okay, now gotta get our pieces here. We need the shell radius and the shell height, and of course our region of integration. Let's go ahead and first figure out what the y limits of integration are. Okay, so we're gonna go ahead and solve this system of equations here. Okay, that's what we have here. We have y equals square root of x and x plus y equals 2. Okay, I want to go ahead and solve this for, so I get a y equals thing in the end here. Okay, so I have y values. So I'll go ahead and write this as, let's see here. Well, I mean, it won't really matter how we go about it. Let's write this as x equals 2 minus y, say. And now I can go ahead and substitute. Okay, so I'm going to go ahead and look here. Take this thing here for x, substitute it in there. Okay. Then I have y equals the square root of 2 minus y. I'm going to undo the square roots by squaring. So y squared is equal to 2 minus y. We shove everything over. Okay, y squared plus y minus 2 equals 0. Little thing on my screen there. Okay. We factor this, so two numbers that multiply to negative 2 and add to a positive 1. Well, we have a y minus 1 and a y plus 2. Does that check out? Well, 2 minus 1 is 1. Okay. Negative 1 times positive 2 is a negative 2, right? And using our zero product property, y equals 0, y equals negative 2, y equals 1. And the one that makes sense here in our picture here agrees what we have from the MATLAB plot is y equals 1. So let's go ahead and circle that because we'll need that. Okay, very good. And now let's think about, and by the way, uh, it should be clear from the picture because we have the bottom boundary as the x-axis, okay? The x-axis is the bottom boundary. We're not going to integrate all the way down to negative 2, okay? The bottom of this solid body here in our picture is y equals 0. So 0 is the lower limit of our integration. Just wanted to clear it up. Okay, now let's go ahead and get the shell radius here. Let's do it here. Shell radius, shell height. Once again, shell radius and shell height will combine both the top minus bottom and right minus left principles. And once you've drawn your picture, okay, you have all your pieces there, right? Take the time in drawing a picture, okay, or using a graphing utility to get a nice picture. And then, if you're working on your computer, you can, paste that into your digital notebook like I have here, annotate it up. Okay. So our shell radius, okay, remember that's going to be the distance from our strip to the axis of rotation. Okay, again, the strip is varying at some position y, and the axis of rotation is the line y equals 0. So the radius is, again, y. And the shell height, here it's really the shell width. Well, we think right minus left, huh? So the right curve is the line, okay? We need that as a function of y here, so 2 minus y. Right minus left, okay? Y equals square root of x, so I may as well go ahead and write this as x equals some function of y, so I square both sides here. Y squared equals x, so I'll get minus x squared there. Okay, hopefully that made sense there, okay? Whenever we integrate in y, we want to make sure we have functions of x, okay? Double check the area between curves video. All right, excellent. Now we got all of our pieces here. Let's go ahead and write our integral. Okay, so we're here. I'll start by writing the integral here. Our volume that we need, 2 pi times the integral from 0 to 1, okay? Shell radius is y. Shell height, 2 minus y squared, dy. Okay, now what do you think we do? Okay, pause the video. Power rule. Well, you got to multiply out first, then you got to use the power rule. Okay, so let's multiply out. Okay, so all those exponents on the inside will increase by 1, 2y, minus y squared, minus y cubed, dy. Now we use our power rule, okay, to get the antiderivative. First term, it's going to be y squared, then a y cubed over 3, then a y to the fourth over 4. Okay, by inspection, you can see that if I plug in 0, I get a 0. And you should also notice that I am a doofus and forgot the 2 pi there. Okay, don't be a doofus. And plugging in 1 is pretty easy. 1 minus a third minus a fourth, because 1 to any integer power gives me 1, okay? And then plugging in 0 will give me 0. That's good. Well, how do I handle all this nonsense here? Well, think about it in twelfths, okay? Or use your calculator. Okay, 1 is 12 over 12. A third is 4 over 12. 12 minus 4 is 8. And then a fourth is 3 over 12. 8 minus 3 is 5. And then 5 times 2 is 10 over 12. Oh man, there's a lot going on here, right? 5 pi over 6 once we clean up all the fractions here, okay? Once again, to get this stuff here on the inside, no shame. Use your calculator, right? Use your calculator. Use your calculator. I got so many of these on the desk here. Use your calculator. All right. Make sure you're plugging in things correctly. We're rolling along. All right. Again, be very careful when you draw your pictures. Okay. Make sure when you're integrating in y, okay, you have functions of y. You have x equals a function of y. All right. That was only the fourth one. But hey, we're making some good progress here. Hey, once again, our favorite parabola. Okay. Y equals x squared forms a boundary curve. Y equals 0 is the x-axis. Let's color that in. Okay. X equals 1. I'll go ahead and do that. So x equals 1 is this vertical line here. X equals 2. Okay, that's here. And we're going to rotate around x equals 1. Okay, that's different, isn't it? Let me go ahead and do that in a solid dark green dotted line here. Okay, and then I'm going to go ahead and draw the arrow. Okay, conflicting greens there. All right, and we're going to go ahead and color in what our solid body is. Magenta region. So we're going to rotate around the line x equals 1. So we're not rotating around one of the fixed coordinate axes here, okay? We're rotating around one of those lines parallel to it. So your factor is going to look a little different here for perhaps which one? Maybe your radius, right? Well, let's go ahead and break it down, okay? Go through the same construction. I'm rotating around the line x equals 1, okay? So if I'm rotating around an x equals h line, a vertical line, if I'm rotating around the vertical line, I'm going to use shells, I'm going to slice parallel. So my little slice here, a bigger pen tip here, okay, that little blue strip, again, is your cross section. But then what does your actual shell look like? Let's go ahead and do that there. Something like this. Now, think about the shell that I've drawn here. Let's say that it's at x equals 1.5. Well, how far is it from the axis of rotation? Well, 1.5 minus 1 is 0.5. Okay. What do you think the relationship should be? Again, go through the construction. Shell radius is the distance from the strip to the axis of rotation. Okay. The strip varies at a position x here. Okay. I almost said y. Careful. The strip is at some position x, and the axis of rotation is fixed at the position x equals 1. Right minus left to get the distance, right? X minus 1, okay? Careful here because the minus sign is built into the formula, okay? So the shell radius is now x minus 1. And that makes sense when you experiment here. Okay? When you draw a couple of representative shells, you should be able to see what the radius should be. Now, what about the shell height? Again, we think about our favorite mantra, top minus bottom, right? For the shell height, Well, the shell height here is nothing really different here. Top curve is x squared, bottom curve is y equals 0, so x squared. Okay, again, draw that picture, top minus bottom. And go back to the area, whoops. Go back to the area between curves video, okay, if you need a in-depth explanation on, again, the top minus bottom and right minus left principle. Nothing left to do but to build the integral, right? But again, notice that here, okay, our region here, let me actually go ahead and outline this whole thing in magenta here, okay? Our region that we're worried about here is this parabola, down here, down, and then up again, okay? So that whole thing outlined in magenta is our region, okay? That whole thing outlined in magenta is our region. Okay. So we're not integrating from 0 to something, now we're integrating from 1 to 2. Okay. So the volume, 2 pi times the integral now from 1 to 2. Shell radius is x minus 1, okay, times the shell height. So x minus 1 is the shell radius. Shell height is x squared. We have our dx there for the thickness, you know. Okay, area function times dx again, okay? Well, just do the same thing, right? Just multiply out. But I want to start the integral at 0. Okay, you can do a u substitution. You don't necessarily have to. It doesn't make it that much easier, but you know, you can multiply it out. Okay, so let's multiply this out. 2 pi times the integral from 1 to 2. X squared times x is x cubed, and then we get a minus x squared. Okay, and we've done this antiderivative already, but with the reverse order of terms, right? It's still the same, right? X to the fourth over 4 minus x cubed over 3. Just use your favorite power rule, right? 2 to 1, and, well, sorry, no vanishing evaluations here. Let's go ahead and write down what you would type in first. Okay. And you punch it in. Okay. Let me do this here. Okay, so that's top, and then minus the bottom here. 1/4 minus a third. Right? Let's kind of showcase a bit of magic here, shall we? So we'll have a 2 pi, right? 2 to the fourth is 16, divided by 4 is 4. Okay. 2 cubed is 8, divided by 3 is 8 thirds. Okay, minus a fourth, then minus minus, that's a plus 1/3. Okay, numbers aren't too bad, right? Well, minus 8 thirds plus a third. Okay, let's think about that one kind of carefully here, okay? Minus 8 plus 1 is a negative 7. But then 4 minus a fourth. Let's think about that, okay? 4 is 16 over 4, minus 1, 15 over 4. Okay, and then minus, what do we say it was? 7 over 3? Okay, and again, you can already punch this into your calculator. Be a little careful here, okay? But this is good practice, okay? Don't go for the lazy evaluation. Okay, go ahead and work it out, right? Make that as an exercise, because then it's a little easier to self-diagnose here, okay? A lot of the times, you might be getting the wrong numbers because you may have mismatched some parentheses here. All right. If we get lazy here, we subtract those two things on the inside. We get 17 over 12. And then, of course, common factor 2 and 12. So we'll get a 17 pi over 6. Look at how nice that is, right? And don't be worried about the arithmetic. Okay, just take it slow, take it easy, all right? You'll be able to get the solution, right? We have another parabola here, but this time it's shifted and it's sideways, okay? Y equals square root x minus 1, okay? As bottom boundary, we have y equals 0. Let's not punch in, okay? There's a square root curve near my face. That's kind of scary. Okay, here we go. Here we go. All right. As bottom boundary, we have y equals 0, the x-axis. Okay. X equals 5, so let's go ahead and draw that in. So x equals 5, I think that's right here. Okay. And we're rotating this around the line y equals 3. Okay. Let me go ahead and that and actually dashed line equals 3. Oh, I've never used this, but this is cool. All right. We're going around that dotted line, that dashed line, okay. And let's go ahead and draw in our arrow, okay? And we're going to go ahead and color in our region, okay? So, again, we think about this, okay? Square root x minus 1 serves as top boundary, y equals 0 as bottom boundary, and x equals 5 as right boundary. So this part here, for solid body, we're going to be rotating around that solid dark green, that dashed dark green line. There's a lot of conflict. I should not use that green. Okay. Let's go ahead and draw in our strip. Again, since we want to use shells, okay, and you can do this with a discs approach. A discs approach, in my opinion, probably is a little easier, but let's demonstrate how the shells approach will work here. Okay, shells I want to slice parallel. Okay, almost said the wrong P word. Okay, parallel. So this is our little cross section. Take a look at that, right? All right, think about what your shell looks like. I'll just draw it in. Okay, good measure. So that's it. Like, okay, not to scale, obviously. We tried. We tried. All right, that's a shell, sort of. And well, again, we got to think about what our region of integration is going to look like. What's our shell radius and what's our shell height? Let's take care of the integration first, okay? So I want to see the y values, okay? So I want to see, I can see that y equals 0 is the lowest, but what about the highest one? Well, I want x equals 5, okay, to be part of that right boundary. So if I go ahead and do that here, so y at 5 here equals square root of 5 minus 1. Ugh, okay. 5 minus 1 is 4, the square root of which is 2. So the region of integration here is from 0 to 2 in the y direction. Okay, we got that taken care of. Now, let's go ahead and think about shell radius and shell height. Again, we'll draw everything here. Shell radius and shell height. Okay. Let's tackle the shell radius first. Okay, here in gray. Well, the shell radius, again, is the distance from the strip to the axis of rotation. And again, shells, you want to think about both top minus bottom and right minus left. Which one here? Well, it's still top minus bottom, okay? Here, the axis of rotation is fixed at the line y equals 3, and the strip is at the bottom, and it varies at some position y. So my radius is 3 minus y. Now, does that make sense? Think about the strip at y equals 2, right? Well, that's 1 unit away from the axis of rotation. Okay, 3 minus 2 is 1. 0, 3 minus 0 is 3. Okay, that makes sense, right? What about the shell height? Okay. Once again, right minus left. The right boundary is x equals 5. And the right boundary is going to be x equals what? Oh, we didn't do the important thing, right? We didn't solve this thing for x, okay? So we square both sides, add 1. So that forms our right boundary, our left boundary, excuse me, y squared plus 1. Okay, go. Now we got everything we need to build our interval, right? The volume is 2 pi times the integral from 0 to, okay, shell radius, 3 minus y, shell height, 5 minus, let's go ahead and distribute that minus through, okay, minus y square minus 1 y, and well, 5 minus 1 is 4, okay. So let's just go ahead and write that in. Y, 4 minus square, yep, there we go. All right. Now, some of you may be concerned that both these have the y's at the back instead of at the front. You can do some manipulation here, but you have to be very careful. I won't demonstrate how to do that. The best way to just go about it is to just multiply it as it is. Oh, we're just going to multiply this as it is. 2 pi. All right, 3 times 4 is 12. We get a minus 4y minus 3y squared and a plus, okay, negative times a negative is a positive, plus a y cubed. Power rule once again. Go, go, power rule. 12y minus 2y squared minus, oh boy, y cube, okay. Add 1 to the exponent, divide by the new one. Plus y to the 4th over 4. Okay, between 2 and 0. Again, evaluating at 0 gives me 0. Okay, and to be honest, I'm just going to be a little lazy here and just defer to my calculator. Okay, so 2 times 12 is 24. Minus, let's see, 2 times 2 squared. Okay, and minus 2 cubed, which is 8. And then plus 2 to the 4th, which is 16 divided by 4. Oh, that just came out to 12. So we have 2 pi times 12, and 2 times 12 is 24. How neat is that, right? Okay, again, once again, picture help you. Get an accurate picture from a graphing utility. Okay, I just did this in MATLAB. You can use your favorite one, your graphing calculator, Desmos, GeoGebra. You know, if you know some Python and know how to use a matplotlib library, okay. Use your favorite graphing utility. All right. Well, this looks funny. Oh, but I don't really have to do a lot of work here. Set up, but do not evaluate. Let me go ahead and box that here. Set up, but do not evaluate an integral for the volume of the solid. Okay, blah, blah, blah. All right, so we have the sine curve, y equals sine x, our favorite parent function. Okay, y equals 0, which I'll go ahead and, again, bold here. That's the center here. That's the center line, the midline. Okay, equilibrium state. X equals 2 pi, all right. 2 pi is like 6.28. MATLAB wouldn't have let me index these in the best way possible, so I just had to use a decimal approximation. So let's see, x equals 2 pi here. And x equals 3 pi. That's 9 and a bit. Okay. And we're rotating around the y-axis. Okay. So the y-axis is where again? Yeah, we should probably bolt that in here. Y-axis is here. Okay, I'm going to go ahead and rotate around there. I'm going to use the dark green here. All right, but now we got to figure out the region that we're concerned about here. So, oops. So, we're looking for sine x's boundary, okay, the x-axis, and then between x equals 2 pi and x equals 3 pi. So it's going to be this little hump here. Okay, and we're rotating it around the y-axis, so we want to use shells. Okay, go ahead and draw a strip. And it's going to be a little too far, so I won't draw in what the representative shell would be. But try to imagine it, okay? Draw like half of it. Something like that. There you go. Very faint. Okay. Once again, we got to think about shell radius and shell height. Okay, I'll pinch in here. Okay, so that we can all see what's going on here. I won't use my finger because it makes the scrolling a little jittery there. So the shell radius, okay, from the strip to the axis of rotation, as always, that's in gray. Shell radius and then shell height here. Top minus bottom. Okay, once again, the shell radius strip is at x. We're rotating around x equals 0. So radius is x. Let's go ahead and put that in there. Okay. Go back, please. So shell radius. Okay. X minus 0. 2 then. Okay. The shell height. Right, the shell height. Again, top minus bottom is going to be sine of x. So let's set up our integral here. Okay, the integral here for the volume is going to be 2 pi times the integral from 0. No, it's not from 0. Okay, again, look at what our region is. Okay, here this is 2 pi. That's 3 pi. We're going from 2 pi to 3 pi. It's a pi here. Okay, very tasty. Okay, radius times height, so x sine x. Sean, you might be asking me right now through your computer screen. How do I integrate that? You're going to have to wait for integration by parts. Okay, this is a prime example of when we would use integration by parts, but we'll get there. But this is the integral that represents the volume, okay? And we're just asked here to set it up, okay? There'll be a task later to evaluate this by using integration by parts. In a similar vein, we're going to set up another integral here. All right, let's go ahead and draw everything in here. Let's draw on my axes here just so it's a little easier for everyone to see. Here's the x-axis, here's the y-axis. Okay, region bounded by, let's see, I have y equals x to the fourth in blue, and then sine of pi x over 2 in orange. Around the line, x equals -1, so that's going to be this line here. Actually, we'll do that in dark green. Okay, around that line, rotating around there, so draw our arrow, and well, going to be this little pink region here. As usual, draw on the strip. Okay, think about what your shell would look like. I won't necessarily draw it in. Okay, shell radius, okay. Distance from the strip to the axis of rotation. Then, of course, shell height. Here we're thinking top minus bottom. So let's put all the pieces together. The shell radius. Okay, the shell radius, okay, is going to be the strip location, x, minus axis of rotation. It's at -1. Careful, because that formula has a minus sign built in. Radius is x plus 1. And what's the shell height? Top minus bottom, right? Orange minus blue here, sine of x. Well, sine of pi x over 2. Minus x to the fourth. Okay? Now, we would need to figure out, of course, where these two things intersect. Now, if you would go through the normal thing and set these two equal to each other, you get a funky looking equation. But you can go ahead and use your favorite like intersection tool here, or use a bit of inspection here. And you can definitely see that they intersect here at x equals 0. You can also see that they intersect here at x equals 1. Think about that, okay? I'll make that a note here. Sine of pi over 2, that's what happens when you plug in x equals 1 there. Okay. Think about your unit circle. Sine of pi over 2, right? 1. And 1 to the fourth? 1. Right? So our integral is set up here. Okay, but we're not going to go ahead and evaluate it because we don't have integration by parts just yet. Okay. 2 pi times the integral from 0 to 1. Shell radius, x plus 1, times the shell height, sine of pi x over 2, minus x to the fourth dx. Okay, this one would still require integration by parts because you have x against sine. But hey, we're just being asked to set up the integral. All right. And that's just the integral that we would evaluate. It'll work with the integration by parts. Cool. Right, for this last question, we're going to demonstrate something that I've been mentioning here for a good while here. Sean, this video is titled Shells. Why is there the word disk here? Is that a typo? No. We're going to find the same volume two different ways, okay? So I have my region here, okay? Our favorite easy-ish upside down parabola, 1 minus x squared. Okay, with boundary y equals 0, we'll rotate this around the x-axis. Okay, so here's our region, our favorite parabola-looking shape. Okay, so I want to find the volume using disks. Okay, let me remind you for disks. Okay, for disks. Okay, you think about the slicing. Okay, pi times the integral from a to b of the radius squared. Okay, if you have washers, outside squared minus inside squared. Okay. But here, the idea is that we slice perpendicular. Okay, for disks, we slice perpendicular. We slice orthogonal to the axis of rotation. For shells, we slice parallel. Okay, the computation here is a little straightforward here using disks. Okay. Now, of course, you'd find the intersection points here. This one is pretty easy to do. 1 minus x squared equals 0. You take square roots. You're integrating from -1 to 1. So with disks here, okay, we'll have pi times the integral from -1 to 1 of our radius, which again, think about it, top minus bottom, right? 1 minus x squared, squared, dx. Yeah, you'd have to square a binomial, do some stuff, okay? There's some symmetry here that you can kind of exploit, which I won't show here. If you know how to exploit the symmetry, excellent. But let's just go ahead and chug through the computation because it's going to give us a baseline. Okay. Multiply this out. Oh, it's a terrible looking integral sign. -1 to 1. This video might be an hour long. That's fine. Okay, thank you for sticking around this long. Okay. And the joke is like, comment, and subscribe. Right. Okay, so you expand the binomial. Your favorite pattern, a minus b squared. Power rule. Okay, so x minus 2/3 x cubed plus x to the 5th over 5. Okay, evaluate that on the boundary. Oh, and I should be mentioning this, by the way. Okay. Whenever I write, say, x to the n over k, all right, that's to be interpreted as 1 over k times x to the n. Okay, same thing. Okay, just want to make sure no one gets lost on that. All right. We use our calculator. Okay. Can exploit some symmetries. Okay, it turns out that when you do the inside thing here, I won't write it down fully. We get 16 pi over 15 volume. Okay. So we have that region, and we're going to be using, and we use disks there. We got 16 pi over 15. But if I slice it a different way, and I get the same volume, the answer is yes. Same curve as boundary, same region. Except now, okay, we're still rotating around the x-axis, but instead of using disks, we're going to use shells here. Let me go ahead and make that a little bigger. There we go. Think about our usual constructions, right? Shell radius, shell height. Okay, shell radius. Okay, if you've been following along, it should be pretty easy to see. But shell radius here. Okay, distance from the strip to the axis of rotation. Strip is variable at y. That's at the top, and at the bottom we have y equals 0. It's fixed. And the shell height's going to take some work. Okay, first we're going to have to go ahead and take our y equals 1 minus x squared and write this as x equals a function of y. So what we do, we go ahead and subtract 1, multiply by -1, take a square root. Technically speaking, there's a plus minus there. Okay. The branch on the right is the plus branch, and on the left, that's the minus branch. So what is right minus left here for shell height? Okay, let's just write down what it would be. Square root 1 minus y minus a negative square root 1 minus y minus minus makes it a plus 2 square root 1. Where am I integrating over? Oh, we hit the hour mark. Where am I integrating over? 0 to 1, right? You can see it in the picture. You can verify that with the boundaries that you have. But let's just go ahead and write the integral using shells, okay? 2 pi times the integral from 0 to 1. All right, watch carefully. Shell radius, y, okay? And then shell height, we have a 2, so let's go ahead and there 2y times 1 minus y, and might be looking at that and be like, hey, wait a minute. I don't quite know how to do this integral yet. Actually, you do. You're a little sneaky. You're a little sneaky. You can actually do this integral. Let's do a quick u substitution here, okay? We're going to map, or basically do what's called a kind of, I don't know if that's the correct name for it, but like a symmetric substitution. Notice that y and 1 minus y are symmetric in a sense. Okay, so we're going to do the u substitution here. U equals 1 minus y, so du is minus dy. Okay, and notice what happens here. When y is equal to 0, u equals 1. And when y equals 1, get u equals 0. Okay. Again, just by plugging into our substitution. So take a look here. Minus 2 pi, okay, times the integral from 1 to 0. All right. And now take a look here. Y, okay, if I solve the substitution part for y, okay, we subtract 1 and then multiply by a minus. 1 minus u equals y. There's a symmetry there, okay? So 2y, no more, is 2 times 1 minus y, 1 minus u, really, times square root u, okay? And now I'm going to employ a little trick here just to make things a little neater, so to say. Okay, we're going to remember that the integral from a to b with a minus sign in front of it just switches the order. Okay, just to make things look a little nicer. So we'll have 2 pi times the integral from 0 to 1. And actually, let's actually go ahead and combine a couple of things here. So the 2, well, that's a constant. That's a scalar. I can pull it out. 2 times 2 is 4. And now check this out, okay? I'm going to distribute. 1 times square root u is a square root u minus u times square root u, okay? U times square root u. We did something like this before. Okay? U times u to the 1/2. That's u to the 3/2. And you didn't need that pesky integration by parts yet. All right. We're going to finish this out because we're basically done here. 4 pi. Okay. Square root of u is u to the 1/2. When we use power rule, 2/3. 3/2 minus 2/5. U to the 5/2. Thankfully, the evaluation of 0 gives us a 0. Okay, when we... Oh, excuse me. If I plug in 1, notice I'll just get, 1 to the 3/2 is 1. Similarly for 5/2. And if we punch everything into our favorite calculator, take a look at this. 4 pi times 4 over 15, which is 16 pi over 15. It's the same. It's the same. You got the same thing there. See if I can do the trick here. Yeah, you got the same thing here. You got the same thing there. Where is it? There it is. Same thing there. Same thing there. Isn't that magical? That was our last problem. Okay, so now we're done with volume. Okay. Main important thing for this is to, draw your picture, start slow. Okay, take your computations really slow. Okay, write out all the steps, try to justify everything with your pictures. Okay. Think of everything in terms of simple things, right? Top minus bottom, right minus left. All we really need, right? And sometimes you can solve a problem easier one way. Okay. That's the thing, okay? Whichever tool is the best for you, go ahead and use it. We're going to go ahead and close out the chapter soon. See you in the next one.